right. I guess you guys can hear me well. I can hear myself. All right. Welcome, everybody, and welcome to my talk. I'm super excited to be here. I'm not used to speak at hacking and industry conferences, and speakers are treated awesomely, while in academic ones, that's not exactly the case. So thanks for the Insomnihack people and the Zanetta team to having me here. One slide about myself. My name is Yanick Fratantonio. I go by Rayhammer on the internet, and I am an academic, at least for now. I'm assistant prof at Eurocom. It's a school near Nice in France, and I got my PhD in Santa Barbara, but originally I'm from Italy. My main research work is on mobile security, mostly Android security, and I did malware things, vulnerability scanning, and things like this. But the last couple of years, I moved to user interface security, and so today I'm here to talk to you about this. I'm also heavily involved in the hacking community and the capture the flag community. I played with the Shellfish and my Santa Barbara team. I have my own team with my students at Eurocom called NOPS, and I had a crazy, terrible idea to join the Order Overflow people, which are the current DEF CON organizers. If you're wondering how it is, it's a bad idea. Do not do this. All right. I don't know if I'm going to be an academic forever, but I love teaching. I recently opened open source, like put everything online about my mobile security class. So it's out there. As of now, I only have slides, but I'm going to put next week some kind of mini war game website specifically focused on mobile security. I'm going to start with reversing apps. People find it interesting on Twitter, so maybe you're also interested as well. So I just want to advertise this. All right. So let's get it started. As I mentioned, today is going to be about UI security. I have two main points about this talk. I want to convince you that UI security matters and that these attacks are real. They exist, they're practical, and it's actually quite difficult to completely remove them. Okay? So, and some of them are considered as open resource problems. Before we start, a little bit on the context. One slide about Android security. Users can install third-party apps. This should not come as a news to you. And third-party apps by default are sandboxed, which means that even in the case you install a third-party app on your phone, it's not that it can do everything it wants. Okay? There are some rules to be followed. For example, each app has private storage. So if you install a malicious app, this malicious app cannot steal your private messages on WhatsApp. Or, there are permission system. You need to ask for permissions to do specific things. And if you want to communicate with the system or other applications, there are well-defined mechanisms so that this communication can happen. Okay? This is very different than usual personal computer or laptops. If I get something malicious on my laptop, and I have Ubuntu in this case, it's usually game over because you can install a user space keylogger, wait that I type my sudo password, get through, and that's it. Okay? So these UI security bugs I'm going to present today are not really interesting on the laptop, let's say, perspective, because, once you get code execution there, it's game over. But on the mobile phones, it's actually quite interesting because even if you get a third-party app that is not behaving correctly, it shouldn't be able to, mess with your other applications. All right. So I mentioned there are security mechanisms to prevent the third-party apps can do bad stuff. And there are many efforts from the Android security team to make sure that they cannot do much damage. There are efforts to reduce attack surface, principle of least privilege, exploit mitigation techniques, and you name it, permission systems, Linux, and blah blah blah. Okay, or restricted access to /proc and similar directories. Okay, if you want to get an overview, there is an awesome talk by Nick Kralevich, who was the previous director of Android security at Google, and basically is very nice overview on all the efforts from the team to improve the security of Android. Now, on the point of UI security matters, what I'm going to show you is that some of these UI bugs and problems can bypass these low-level mechanisms that are now in Android. Okay, and I believe that this Android UI is the Achilles heel, in a sense that apps can have full control on the screen, they can do some tricks, and I believe these bugs are not well understood. And so if I find a bug and I report it to Google, it's not as easy to get patched as I would reply, maybe when I submit a buffer overflow potential problem. And I'm going to have a couple of nice stories to show that this is actually the case. I also believe that the missing, what we call trusted UI, is one of the missing pieces to make these mobile devices more powerful, able to, for example, control security, critical systems, medical devices, or electronic IDs, and so forth. Okay, so I believe that focusing on this, fixing this kind of resource problems may help us get mobile devices even more useful than what they currently are. Okay, so in terms of UI attacks, there are two big categories I'm going to present in a bit, but conceptually, I would like to define what I mean as a UI attack. I mean any attack involving the user interface that somehow compromises or affects one of these confidentiality, integrity, and availability. Okay? And usually these attacks are about deceiving the user. Okay? What I like to focus on is what I call imperceptible attacks, or impercettibili, if you're Italian. And the idea is that once these attacks are run, even if you're a security expert, it's very difficult to know what's going on. Okay? Even in the case where you stare at the screen on your phone, like you're usually staring at the screen of when you visit your interesting websites. Okay? So it's like, when like a magician telling you, I'm going to trick you, similar things happen here. We actually did a user study with some of these attacks, and nobody was actually able to understand that an attack was run. Just to make sure this distinction is clear, an example of non-imperceptible attack that I would consider is web phishing. Web phishing is about, tricking the user with some UI tricks, trying to make sure the user believes this website is actually kind of like Facebook, but it's not imperceptible because the expert has a way to figure this out. You can check the green lock, you can check the domain name that points to facebook.com. So there is some kind of technical way to make sure you are safe. While for some of the attacks I present, that's not the case, that's why I find them interesting. Cool. So there are two big classes of attacks. The first one is clickjacking. In clickjacking, an attacker lures the user to click somewhere and to make him do something stupid. And the classic goal is privileged escalation or confused deputy. The second big category is phishing, where the attacker tries to convince the user to put his username and password, credit card numbers, and things like this, where he should not put them, in a way that the attacker leaks them and can steal them. Okay? It's not only limited to this, there are a number of tricks and twists to these attacks, and some of these involve messing with password managers and instant apps, as we're going to see today. So we're going to start with clickjacking. I have one slide, like a overview on this. Before we start this, there is one Android permission that is very important for this presentation. Informally, I call it draw on top. Technically, it's called the system alert window, if you are familiar with this. If you have this permission, you can draw arbitrary windows or overlays, as they're called, on the screen. With arbitrary, I mean literally arbitrary. You can decide the shape, the content, if it is transparent, playing with alpha values, and the actual position. Okay? Extremely powerful. Not only this, you can also control how this overlay reacts to clicks. Particular, you can set up these overlays through some flags in a way that the overlay is either clickable, XOR, pass-through. So either clickable or pass-through. Clickable means that if you have an overlay, and the overlay is clickable, and the click reaches the overlay is receiving a callback saying, hey, the user clicked here. But it cannot be propagated below it. Okay? Pass-through is the opposite. The click, even if the user clicks on the overlay is not notified that there is a click. It doesn't know where the user clicked, but the click goes through and reaches what's on the bottom. Okay? This is XOR. You cannot do, you get the click and then you propagate it due to very simple reasons. If you could do this, then it would be easy to actually create a number of overlays on the screen, invisible, and somehow track what you're typing. Okay? Because you can just understand where the user clicked, and then you say, okay, he clicked here, you log A, press the button A, and then you propagate the click on the real keyboard, so you can do some kind of UI man in the middle. For this reason, you cannot do this. It's XOR. Okay? This permission is not rare. It's used quite often. And when we did this study, 10% of the top apps were using this, including big apps, Facebook, Skype, Uber, and things like this. Okay? And at least when we did the study, it turns out that this permission is automatically granted if an app is installed from the Play Store. I have an asterisk here because I've heard rumors that maybe it's going to change in the future, which is for me is very interesting because Facebook is used by 1 billion people and they cannot really ask now 1 billion people, hey, please enable this permission. So my guess is that they're going to introduce some kind of whitelisting things for big apps can do this and small apps cannot do this, which I think is a bit controversial. It could be a bit controversial, but that's the current state. And anyways, it's a permission, so app can actually ask for it and so forth. That's a couple of examples. So now this permission is used. That's my mom pinging me on Facebook Messenger. So Facebook Messenger, you created these annoying bubbles, and now you know how they are created with this permission, okay? That's another category of usage of this permission. These are called screen filters. These apps have the only purpose of creating a reddish overlay on top of your screen so that you can watch your phone and play with your phone just before going to sleep, and the phone is not going to mess up with your sleep schedule. Okay, so it's going to remove some color component known to affect your sleep schedule, and that's about it. The only role of this app, in this case, is called Twilight, is this. Okay, and it's all based on this draw on top permission. So this permission is not going to go away anytime soon, and we need to stick with it, and then we try to understand what we can do with this permission. Now, I have one slide on what traditional clickjacking look like. This has been known for a number of years now, and it works like this. Let's say that you are an attacker and you want to gain additional permission. In this case is accessibility service menu, and you want the user to click OK. Now, if the user is not completely dumb, he is not going to click on the OK. Okay. So the clickjacking trick works like this. The malicious app, before switching to this accessibility service pop-up, it creates a full screen overlay with a fake button. Then below, it actually pops out the accessibility service thing. And now it creates this click here button in a way that is passed through, so that when the user clicks here, the click actually goes on the bottom of it, and the malicious app actually gets the permission. Okay? Again, this has been known for a number of years, and I'm gonna show what Google did about this and what kind of protection mechanisms are there, but that's basically the idea behind clickjacking. Now, a couple of years ago, I started working on this topic, and the first question I asked myself was, what about multi-step clickjacking? There are some attacks for which you want the user to click here, here, and here, not just one click, okay? And turns out, it could be useful. There are some scenarios where you want to eject multiple clicks, and there are a number of challenges. The key point is the malicious app needs to understand when the user clicked on the target button, so that the malicious app can somehow rewrite itself and reorganize the overlays to convince the user to click somewhere else. Okay, and what if the user didn't click on the target button? The malicious app wants to know it so that it knows it does not need to go to the next step. So just by monitoring clicks is not enough. And it's tricky because in clickjacking, by definition, the click of the user needs to land on the victim app, not on the malicious app. And as I mentioned before, if the click doesn't reach the malicious app is not notified. Okay? So it's not easy. And turns out there is one flag with which you can create these overlays called flag watch outside touch. So at that point I was like, okay, I found a way. And if you create the overlay with this flag, basically you get notified even for clicks that do not reach your application. However, the coordinates are set always to 0, 0. Again, it's a protection mechanism so that you cannot track the user when he clicks outside. So again, you're stuck with, okay, I know the user clicked, but I don't know where he clicked. And then it came to mind, so there is still the problem, right? Because you don't know where the user clicked, and it's a very important step for doing these kind of multi-step attacks. One trick we found, we call the context-aware clickjacking. So the attacker doesn't know the coordinates of the click, but what if there is only one way for the click to not reach the malicious app? It's actually much easier with an example. Let's say we want the user to click on this target button. The attacker could do this. You create a number of overlays in a way that the clicks does not go through, and you create only one overlay with which the clicks actually go through, is passed through, okay? And now think about this. If the user clicks here, you get the coordinates because the click is on the malicious app. Same here, but if you click here, you get 0, 0, and this is enough to understand the user click on the hole. Okay, so this trick works only if you have one specific hole. You cannot generalize this to two because otherwise there is ambiguity. But for clickjacking, this is actually enough. And so you know when the user clicked on the target button, and you know now you can rewrite yourself the UI so that the user is pushed to click somewhere else. Again, that's a research paper where we found these bugs. Okay, so I mentioned that clickjacking is actually quite old, and of course Google didn't stay there and look at it. So there is a security protection. It's called the obscure flag, informally. Okay, this obscure flag works like this. Whenever you have a button, the user clicks on it, he receives a motion event. Now they added a flag called flag window is obscured flag for this event. This flag is set if at the moment of the click there was an overlay on top of the button. Okay, so basically it's the receiving button that somehow can understand, wait a second, there was something on top of me when the user clicked, so maybe the user didn't see the button or anything, and so it may be confused, I'm going to reject the click. Okay, so the app can implement this logic saying, this is suspicious click, I'm going to reject it. There is another way you can set all the clicks on the view with this method, so it's this is the main security mechanism against clickjacking. This is how it works in action. So see, this is the view from before, where we wanted the user to click on the OK button. It is fixed now with this obscure flag. So let's say we create an overlay on top, just for explanation purposes. And let's say the user clicks here. Now the settings app is going to reject the click. It's going to show some pop-up that is going to say, because an app is obscuring the permission request, settings cannot verify your response. So the user is asked to disable all these overlay things, and now you can click on it. Okay, so that prevented clickjacking for a while, and then we found a way to bypass it. The bypass is actually quite simple. This is a trick. What about, so the obscure flag protects the OK button, but what about covering everything except the OK button? You do this, and that's about it. And it's quite easy to convince a user to click on the OK button. These OK buttons, these buttons that are protected from clickjacking usually are very generic. It's like OK, enable, and things like this. Okay. So here the conceptual trick is that by hiding the context, we can still lure the user to click where we want. Okay. Now, in this story of what you can do with clickjacking, in this research paper, what we show is that these simple tricks are enough to get from this drawn to permission to a CBD service. For those of you that are not familiar, CBD service is a mechanism that in theory is used for apps to assist users with disabilities. Okay, and it's super powerful mechanism in a sense that it can be notified whenever there is a UI event. So if there is some text that it changes, an app that accesses accessibility service is notified about this, and so it can read maybe the text back to the user. And the app can actually inject UI events, such as clicks. So that basically maybe if the user with disability has some kind of additional device, like a touch keyboard to the phone, this accessibility service is the mechanism that is used to actually inject the clicks around. So it's very important, and it's something that Android has and is going to be there for a while. In theory, it's powerful, but it shouldn't be God mode. So if you check the documentation, there was written something like this. Since this is a documentation of accessibility service, what kind of events you can be notified about, and they were saying, privacy could be compromised by leaking specific things like passwords. So if you try to get the text content of a password field, you're not going to get it. It's going to be empty string. And it's true. If you try to do get text on a password field, you always get empty string. So there were some limitations, and then we checked around, and it seems these limitations were quite easy to be bypassed. In a sense that if you have this username and password field, even if I type the password, then I go get text, is going to always be an empty string. However, the keyboard itself is a tree that is a normal application. So whenever you're actually pressing on a key, the system was advertising as a broadcast, hey, what's up? The user just pressed on key R or key A and so forth. And so basically, true, you cannot get the password, but the keyboard itself was treated as a normal app, and you were basically able to read the password from the user. We kept investigating, and we found that basically nothing was protected. Google Authenticator tokens. These guys, it's actually pretty nice. There is also an embedded refresh functionality, so that when this changes, there is a new UI event, and so you get notified, hey, there is a new token. So they expire, but you get always a new one. My favorite was the security pad with which you unlock your phone. Turns out this is treated as a normal application. So if you click on a button, the system is going to broadcast to this accessibility service application, hey, the user just pressed on number 1. So we show that you could steal the PIN, Awesomely, you can also inject the pin and unlock the phone automatically. And the cherry on the cake was that we could do this while keeping the screen completely off. Somehow, the thing that checks, oh, should I turn on the screen on, was not triggered. And so once you're compromised, we can actually inject everything, do whatever we want, lock the phone again without having the screen popping out. So it's completely stealthy. I have a quick demo with a video. This is going to show you how we trick users to actually enable this CBD service. And the slide before just show you what you can do with a CBD service. And this is also part of the user study we did. So we tried with real users. And let's see how it goes. Basically, we ask our user subjects to play with our application. And the application was something like, it's going to be a tutorial on how to be a nice person. Okay? And so we ask them, okay, press start tutorial when you're ready. And then we tell them, you're going to show something. And in this presentation, humans are going to be represented as a green droid. Press next when you're ready. And then we told them, we're going to show you a video. And it's going to show you what happens when you're not a nice guy. Please press OK. And when the user presses OK, a video starts. Okay? And so it's a very dumb video. At this point, a CBD service is already enabled. Okay? And what is happening under the hood is that somehow we are automatically clicking around through a CBD service and install another application, enabling all permissions, device admin, and leaving all traces of the compromise that just happened. Okay? At this point, the attack is already over. So now I'm going to show the same video, but with these overlays on top, drawn semi-transparent, so you can actually see what was going on. The first button was about selecting our own application from the CBD service menu. The next button was about trying to enable it. And the third one is the OK button you've seen before, with the whole, because there was obscure flag. So this is a live demonstration of how you can bypass the obscure flag. At this point, we are already installing a malicious application. We are enabling device admin. Super relaxing. We are enabling all possible permissions. That's my favorite part. And since we're pros, we are clicking on recent and swipe everything off, so there is no sign of any compromise. And at this point, the attack is already over. There is a third-party app installed from, in this case, it was from the SD card, and that's about it. I have another quick example, is a small variant, on how you could create a ransomware case. It's a different one in the sense that we get the pin from this CBD service tricks, and then we show that very fast you can use this pin, change it, and reboot the phone. And at this point, the user is locked out. Eyes open. This is very fast. So we started. At this point, we just injected the pin we already know. Here we are changing it. Now we're putting a message for the user so he knows who to pay, and that's about it. After this reboot, the phone is completely locked. All right, so we notified these bugs to Google, and Google came up with a new defense. It's called hide overlays. Okay? Hide overlays is super simple. If you now go on this CBD service menu, automatically all overlays are completely hidden. Okay? So conceptually, this works because the user cannot be deceived, and now you cannot confuse him anymore. Okay? So these attacks of getting a CBD service does not work anymore due to this fix, but let's dig into this a little bit more. So I believe these tricks work, and I think is enough to prevent clickhacking. The problem is that it's not very widely deployed. Why? Well, it seems that only system apps can use this trick. And it makes sense, because if you have a third-party app with the power of removing all possible overlays, then you can think about other attacks, denial of service and things like this. So as of now, this hide overlays trick is only used, as far as I know, from a CBD service settings, from the menu when you select the permissions and similar things. Okay? And that's about it. So third-party apps cannot really protect themselves with these tricks. Then we start asking more questions like, okay, what about this obscure flag? Because it's true that you can bypass it, but at least it raises the bar, because you need to leave at least the button quite visible. And then a friend told me that, we actually tried to use it in production with a very big app, let's say, and it did not fly. And tons of users start complaining about, oh, my phone is broken. Twilight, screen filter apps, once again. Turns out that if these apps are actually creating an overlay, then every button protected by the obscure flag cannot be clicked. And so this creates problems. And so when this protection mechanism with obscure flag popped out in Twilight, Twilight need to tell users, if you need to enable permission, you need to disable this. And it was framing this obscure flag permission or protection system as a bug. The fix they mentioned here, fix in Android in Android 7, because then they would automatically hide all overlays, but it's not an actual bug, it's actually a protection mechanism being used. But so what about all the other applications? Turns out that it's still a widespread problem, and apps don't really have a technical way to solve it. So we try to check more targets. Turns out the Play Store was also vulnerable. You can eject a click here, you wait a little bit, and then you ask the user to click again on the same position, and that's going to be the open app. So you can install it and open with 2 clicks. And then we check the Gmail. With an intent, you can create, open up a composed message like this, where you set the to, the subject, the message. And so just ejecting 1 click, you can send arbitrary emails on behalf of the user. Google Authenticator. You can do long click clicking. If you convince the user to long click somewhere, the token is actually copied in the clipboard, and then you can get it. Similar things with, Twitter, Facebook, it's all vulnerable. Google Drive, if you long click on something, I think it's going to be share the folder, for example, and it's going to copy the link on the clipboard, which the malware can access. Signal and WhatsApp were also vulnerable. With this Signal, the trick was that with a bunch of clicks, we can convince the user to send a message to an arbitrary user, which means an attacker could leak your telephone number. We also found another attack that doesn't work anymore, where basically we could initiate a backup, backup procedure on Signal. In previous version of Signal, this backup would be unclear on the SD card. So by just ejecting, I think 2 clicks, we're able to get all the plain text messages, telephone numbers, and things like this. Signal goes smarter, and now what they do is to create this backup with the password, and the password is displayed on the to the user once this backup is completed, so at least it's protected. Google Chrome, all the click jacking protections we have for web. Google Chrome, the actual app, of course, they're still there. Lookout security, I don't want to pick names, that's what we try, but of course all the other apps are vulnerable as well. So it turns out that the problem is, again, backward compatibility reasons. They don't want to use these protections because they would screw a lot of people up. And when we disclose these bugs to these vendors, they actually replied accordingly. Twitter, we try to think about this, but we cannot do this because of UX issues you mentioned. So we did our job, so we tell them these are the bugs. We also told them, pay attention. Friends of ours tried to deploy this with another big app, and they couldn't for these UX issues, so think about this. And they agreed it was not possible for them. Signal, they told us the same. Without the actual effective mitigation, we cannot do anything. And so these bugs are left unprotected. Facebook, WhatsApp, Instagram, very similar replies. Like, we have a threat model to consider and pros and cons and so forth. And again, all these guys are not patching this for backward compatibility concerns. It is somehow an open problem. We try to do our part. So we published an academic paper where we outline how we would solve it. The conceptual trick here is to try to distinguish between, malicious overlays like semi-transparent that are okay and maybe more opaque overlays. But this requires framework modifications. So we pitched this to Google. I don't know what's going to happen. And it makes sense that they're refraining to actually deploy this because they will need to change how the rendering procedure and things like this is not simple. But I think it's considered an open problem. Okay, so at the beginning of the presentation, I tried to say that these UI security bugs are not like the other ones. If I find a buffer overflow, people are going to fix it fast. With these bugs, it's a bit more complicated, and I believe it's not really well understood. For example, the obscure flag, the bypass I've showed you is pretty simple. You just hide everything except, so I think we found it not because we are super smart, but because nobody else thought about this before. We also found there is a bit of misleading documentation. That was quite funny. So we checked the docs, and the doc said, this flag is going to be set to 1 if there is a motion event that is partially or wholly obscured. This partly is actually live, and you can try to hide to cover a part of the OK button, but as long as the click goes through the part that is not hidden, then the flag is not triggered. The funniest part is that we had proof that Google knew about this by checking the source code. There is another flag called flag window is partially obscured. If you check the docs, this top part is absolutely the same. The only diff is, unlike the other flag, this is actually true. Funny part is not true even in this case, so I think this flag was never used, and they're just to convey these are difficult problems, and it's known thing internally, but it's not easy to actually fix. And again, maybe it's actually easy from an algorithm perspective to fix this, but I think it will cause so many UI problems and maybe battery performance problems and things like this that's why probably we are still at this point. I also found another trick about the obscure flag, and for this I felt extremely proud. So I think it's pretty neat. So I'm gonna show you it today. This is actually fixed with an attack that we called invisible grid attack. With this attack, we could record all possible keystrokes, so we can record exactly what you're typing, and it only relied on this draw on top. I showed you if you have a CBD service, it's game over already. This attack only worked with this draw on top. The key point was to abuse somehow this obscure flag in an interesting way. The attack works like this. Imagine this is the phone laid down, and then conceptually the attacker will create a number of overlays organized in this way. 1, 2, 3, 4, one on top of each other. Okay? Good. Now, these overlays are created invisible. So once this attack is running, you don't see them. The clicks are passed through. So if you click on top of them, everything works as expected because the click reaches what's on the bottom. And we use this flag watch outside touch that I mentioned before, which means that when the user clicks somewhere, since the click doesn't reach the malicious app, it reaches the victim app on bottom. All the clicks are considered outside. So each of these overlays is going to receive a motion event. The coordinates are set to 0, 0. So we don't know where the user clicked, but you get a motion event. Okay. And the goal for the attacker is to understand where the user clicked. Turns out the obscure flag is actually set accordingly, and the algorithm somehow works in this way. Let's say the user click on number 1. The code computes the height of the impact point, and then each overlay compares the height of itself with the impact point. So for example, one says, impact point is basically myself, so I'm fine. And so not obscured. Number 2 is going to say the same, or, my height is actually higher than the impact point, so there is no problem for me. And 2 and 3 and 4, they do the same. However, if you click here, the impact point is actually going to be higher than the layer 1. So for layer 1, it's going to receive obscured, while the other one is going to receive not obscured. And now I guess you understood the trick. Depending on where you click, these 4 motion events are going to contain a different patterns of this obscure flag and not. And this is enough to understand where the user clicked. So for each click, you're going to get n, where the n motion events, where n is the number of overlays, and depending on the pattern, again, you can see, okay, the user clicked here or there. The beautiful part here is that we are using a security mechanism as a side channel. And this was enough to basically understand where the user clicked. Of course, to weaponize it, you just create many overlays, one on top of each key, organized as I showed before. And during an attack, of course, this is all invisible, so you don't see anything. And then you basically have a live stream of what the user is typing. This was patched, so this is one or more categories like, okay, that's we know how to patch it, but I found it super interesting. Another story to convey that these UI security bugs are not, it's not very, very easy to, get them patched is the following. We, told the Google guys, on documentation that is written, you should not be able to get the passwords, but look at us, we got all the passwords. So the reply was won't fix, work as intended, at which point I was a bit, what's going on? And then, they changed their mind. Okay, high severity and everything is fine. Fantastic. And so I was very happy. After a month, they actually changed their mind and said it wasn't fixed because limiting the services would render the device unusable. Which for me is very surprising because they kind of admitted it was a bug, but they cannot actually fix it. So the label was this won't fix work as intended. So I was really upset. You cannot tell me work as intended. And so eventually I think they gave up and they reply, we will update the documentation. The awesome part is that they did, so kudos to them. And I have here the link to the web archive, whatever. You can see there is a security note mentioning this, and then it got silently dropped. So it's an awesome instance of patch the documentation, not the code. I'm still waiting for my CV for the 0 day in the docs. I don't know. Hopes are last to die, so we'll see what happens. Again, this is a stupid story, but it's just to convey, it's not just finding a buffer overflow. It's more complicated because these are not well understood and there are problems like this. Okay. So in the last part of the talk, I would like to focus on more things on phishing. The key problem that makes phishing very interesting for mobile is the following. Check this out. This is the original Facebook application asking you for username and password. Or is it? I don't know. You have no idea to understand, you have no clue to understand if this is just the spoofed UI or if the real Facebook UI. On the web, we don't have this problem because the expert has always a place to check for the gridlock and to check that the domain name actually makes sense. On the UI or mobile, there is no space for this. There is no PKI for package names. There is nothing like this. So the user is left wondering, is this a real Facebook or not? And this is the conceptual problem that makes this interesting. So a basic phishing attack on mobile would work like this. Let's say the user is opening the real Facebook application. In the background, there is the attacker tries to understand whether the user just opened the Facebook application. So it would query for some proc, get running task APIs and things like this to understand, did the user just press on the opening Facebook app? And if that's the case, the attacker would just pop on top and would just show a spoofed Facebook UI. Now, once again, these are attacks being found 3-4 years ago. So on Google's side, what they did was to somehow try to find all these possible side channels and cut them so that now malicious apps cannot really understand, hey, the user just opened something. It's an arm race because, you can have bugs where other APIs expose this information, but that's more or less how they fixed it. And then we had a research paper 6 months ago where we tried to explore the next step of mobile phishing, try to understand how modern features can be maybe abused in this context. And so we started with mobile password managers. And what we found was the following. They actually work for mobile as well. I use it on my laptop for my browser. I'm not a mobile password manager user, so I was a bit surprised they actually work very nicely as well. If you open the Facebook app, they actually would pop up and telling you, hey, I know your password for Facebook.com. And if you click here, I'm gonna, autofill your stuff for you. And then we kept asking ourselves, how can a password manager link Facebook.com with an application on your phone? On the browser, it's actually an easy problem because if you have, credentials are born for the web. If you have a username and password, they are for Facebook.com. If you go on a website, the LastPass or password manager can check, is this LastPass.com website? On mobile application, you have package names, you have different things, but you don't have Facebook.com. So we found this interesting and we start asking, how do they do this? Turns out password managers work with 3 different technologies. They choose one of these. The first one is accessibility service. The thing I mentioned above, yes, password managers are using this to automatically understand which app is on top and filling username and password. Google understood this is a problem because in theory, accessibility service is used for people with disability. So they come up with a new framework called Autofill Framework. It works similar way, supports password manager to do these kind of things. And there is another modification of the framework, modification or protocol where you modified both the client and the server, and then they can exchange username and password. This stands for, I think you only log in once or something like this. It turns out that for all the password manager we found, and for all these techniques, the package name is the starting point to map an app to the website, the package name. Now, if you know anything about Android, you should be terrified and screaming about starting from the package name because it's not like the web. Package names are not supposed to be trusted. Nobody's checking for them. Okay, so there is no relation between package and sub-package, and some password managers believe there were. For example, it's actually quite easy to get Facebook Evil application on the Play Store. We actually tried. The only constraint is that there cannot be 2 apps with the same package name on the store and on the device. But other than this, is basically the world, far west. Okay, you can do whatever you want. Now we actually try to understand how password managers try to get from some package name to the target domain names. And okay, we check Dashline. Turns out they have some interesting heuristic. They take the package name, they split it by dot, and then they check if these small components are actually part of a target domain name of credentials they know, and if yes, they're going to suggest it to you. So you can have stuff like this is going to trigger a suggestion for Facebook.com, or this is going to trigger a suggestion for these 3 websites. So you can be as creative as you want. LastPass, they fell for it, so they were checking that the package name had some kind of common suffix with the website. So they was actually getting common Facebook people, flip it, and see if there was some common suffix. So this is enough for an app to trigger auto-suggestion from LastPass about Facebook.com. They also had a part where they would crowdsource this mapping, and so we were able to download this from their database, and there were things like weird package name associated to private IP addresses and things like this. So it seems they were not very monitored. Another example was Keeper. This is awesome. They take the package name, they build the URL that points to the Play Store page, so this one. Then they parse it, and they parse that this is the website. And yes, they're treating this as the main website associated to this package name. And of course, if you have a Facebook page, you would put facebook.com, whatever. That's enough to trigger auto-suggestion for Facebook. And of course, it's absolutely not trusted. You can put whatever you want there. So the next step, we also found out that you have username and password, but what about this? You write your UI so that the password is not visible. And yes, it works. You would have password managers auto-filling also the hidden field. How do you hide it? We tried to come up with a number of tricks, and they all worked. You put very small area or the same color foreground, background, you make it transparent, you actually set it to gone. This stuff is actually working, okay? So this password manager stuff is not that you would open the app and then automatically they steal your username and password. The user still needs to click. But I believe that if you have a malicious app and then the password manager is full, the user is more likely to be, fooled as well, because this password manager auto-suggestion somehow add legitimacy to the actual phishing attempt. And again, from the user perspective, there is no way to understand if it's the real Facebook app or not. Another technology we tried to check was Instant App. For those of you that don't know, it's a new technology in Android. You can try apps out without actually installing them. So if you have a phone that supports this, you would have a try now button. You click on it and the app somehow runs on your phone without the proper installation so that you can try it out. The flow works like this. You can also associate instant apps to URLs. So if you go to a specific URL, there is a way to convey to the Play Store, hey, show them a suggestion to install an actual application. So if you go on the URL, then something like this will pop out and the user presses open up, waits 2-3 seconds, and now you have an application running on your phone. This is relevant for phishing because you have full UI control, okay, starting from a link. So it doesn't require a full installation of an application. And so in the paper, we showed that you can have an end-to-end phishing attacks combined with these password manager tricks, where basically you go to some, fake website and we ask to, pay with PayPal. You click on this. This would trigger a prompt for installing an instant app. You click on it. This, of course, is our malicious application. You wait 2 seconds, and now you're on the PayPal app with LastPass or other password managers suggesting you to insert username and password for PayPal. And of course, this was our app, not the real one. Okay? Turns out there is a right way to implement this web and package thing mapping. It's called digital asset links. This for Android. iOS is a similar technology where a website can say apps signed with this certificate and with these package names are okay. For example, for Facebook, there is a link like this. And if you go on this, you're going to find something like this. This is my trusted package name and this is my trusted certificate. Turns out only 2% of the names that we had actually use this technology, and that's why password managers, as of now, cannot really do a better job than what they do. So, of course, we communicated all the issues. Their fix is to just say to the user, we cannot verify the trust link, please pay attention. Okay, but they cannot do better than this as of now. All right, and again, there is a research paper on this topic. So, I have last couple of slides on the future of UI security. There are a bunch of open problems that they find interesting. So, understanding what kind of application I'm interacting with, or, how can an app understand if the user clicked there intentionally or not, or, preventing about the OS, or understanding whether the content is actually trusted or what is shown, and so forth. And some of these research areas have been explored already, and Google is doing some step forward. For example, in latest Android, there is a Android protected confirmation. It's a new API. It's awesome. They basically, from Trust Zone, they can render something to the screen and ask something to the user. And then in combination with Trust Zone and attestation tokens, they can prove to a remote backend that the user have seen this message, this specific message, and that the user pressed OK through Arbor button. Okay. The details are a bit complicated, but I just want to point out there is some kind of movement in the UI related features, and they are super interesting. And again, it's always evolving. Another API that just popped out, there are just documentation as of now. It's going to be maybe in Android Q, is about identity credential. So with this API, people could support the usage of mobile devices as trusted driving licenses or passports and things like this. Again, they combine Trust Zone and attestation tokens and things like this, so cryptographic signatures and things like this. And I think this is just the beginning, and I'm super excited about this. Last point I want to make is that even the rules are changing. I mentioned before that this drone top permission is or was automatically granted to applications. For sure, I think it's going to be always granted to big applications. I don't know if something is going to change with the smaller ones. But again, Google is trying to take actions on this permission abuse. And another interesting point that I've read, I think 2 days ago, is that maybe in Android Q, it could be that apps cannot just pop out from the background. Okay, and if this is true, it's going to have great impact against adware, because you cannot just stay in the background and wait and then pop out the advertisement. Or even the phishing attacks, I mentioned, the ones that stayed around and check for set channels, they cannot just from background to create an activity and get UI control. As of now, it's rumor. I think I've seen only one small article on the topic, but there is some kind of evolution even in these things. All right. Was like to acknowledge my students, work with me on these topics, Android security team, they're awesome. And all the developers of the password managers, their replies were always super professional and timely. And so we're very happy to have been working with them. Just some links for the papers. I'm going to upload the slides later on, so you can click them. And that's about it. Stay tuned for this war game style stuff for mobile security. And I think I'm done. Thank you very much.
Thank you, Yanick, for your interesting talk. Is there any question? We just have time for one or two, maybe. Yes.
Thank you for the very interesting talk. What was the fix for the invisible grid problem?
Oh, I think they stopped propagating the obscure flag for these motion outside events. Because if you are protecting yourself, the click would need to land on your application, and this motion outside is only for clicks that land outside.
Thank you.
Hello, thanks for the interesting talk. Do you know if this problem also happens on other mobile platforms like iOS or? Well.
My understanding is no, because this drone top or the accessibility service, my understanding is that they are system level permissions. So I think third-party apps cannot even get them. And the basis for these attacks is this kind of abusing these permissions. I'm not sure about the popping up from background, but I'm pretty sure you cannot do this. I'm not an iOS person, but there is a talk from an iOS guy later on today. So you should bug him with this question so that I also learn things.
Thank you.
Yeah.
Last one.
With this obscure flag telling applications that it's been covered, wouldn't it help if the application also received information how many % of the screen is covered? Because in this case, the application could, for example, only allow something covering everything, or maybe less than half of the screen.
Yep, that's a good point. Maybe you could do this. I think it's weird for Google because they would need to disclose more information to third-party apps, and you never know how they can be abused. Unfortunately, metrics like, if the 50% of the screen is uncovered, then you're fine, is not enough, because the trick could be that, for sending weird emails, you can just cover the actual message. So you can cover like few pixels and then still win. Attack against the Play Store is you have the price, you can modify only few pixels so that the price changed, and still this attack works. The tool we try to add, that we discuss in the paper, tries to have a heuristic to say there are some pixels modified in not uniform way, and that's how we think we can address this. Yeah.
Okay, I think time is out.
All right. Thanks a lot, guys.